IXIA, a leader in performance analysis solutions, presents the IxNetwork video tutorial series. IxNetwork is IXIA's flagship software application for testing the network infrastructure, including all devices like routers, switches, network access controllers, broadband access, carrier Ethernet, and data center Ethernet. It's used by professionals around the world, including development and system test engineers, network design and support engineers, and even marketing and sales to demonstrate product capabilities and performance. This video tutorial is brought to you by the IxNetwork product management team.
In this IxNetwork video tutorial, we will cover IXIA's new TrueView Convergence. The TrueView Convergence is IXIA's patented convergence measurement methodology which accurately helps users measure convergence time from a triggering control plane event all the way to a data plane switchover. As a part of this video tutorial, we will go into 6 different chapters. In Chapter 1, we will cover the test topology, which includes 3 ports connected to a device under test running OSPF. Of these 3 ports, OSPF is running on 2 of the ports and is advertising overlapping routes, one router advertising the route ranges with a higher metric and another one with a lower metric. Chapter 2 will walk us through basic configuration within IxNetwork to set up this topology. In Chapter 3, we will explain in detail IXIA's TrueView convergence testing methodology to calculate control plane data plane convergence. As a part of this chapter, we will go into a lot of detail with regards to terminology used for all these convergence measurements and the convergence methodologies as implemented by IXIA. In Chapter 4, we will go through all the convergence options that need to be enabled in the IxNetwork 540 release to trigger this TrueView convergence measurement. In Chapter 5, we will build traffic so that we can accurately run the convergence tests. We will get into detail on how to set up the source and destination traffic meshes and what specific tracking options need to be enabled as a part of this TrueView convergence test to get accurate microsecond level accuracy for convergence times. In Chapter 6, we will spend some time in getting into all the detailed convergence calculations which are included as a part of the IxNetwork 540 release and where these statistics can be viewed within the GUI. Chapter 1. The test topology. In this chapter, we will explain the test topology used for the remainder of this video tutorial to indicate how IXIA calculates convergence times. The objective of this particular test, as mentioned, is to accurately measure, using IXIA's TrueView convergence, the convergence times for a triggering control plane event all the way to a data plane switchover. In this test setup, we have 3 IXIA ports connected to a device under test. Of these 3 ports, OSPF is emulated on 2 of the IXIA ports. Each port emulates a single OSPF router advertising a single route range. Both the routers advertise the same route range, with OSPF R1 advertising all the routes within the route range with a lower metric. OSPF router R2 advertises the same OSPF route ranges to the device under test but with a higher metric. The purpose of doing this is that the device under test will forward all traffic destined to the routes advertised by OSPF routers R1 and R2, but because OSPF router R1 advertises the routes with the lower metric, this will be chosen as the primary path. We will then trigger a control plane event, which is an OSPF route flap on R1, which will then make the DUT switch all the traffic destined to the routes advertised as a part of the route range to the alternate or the backup path advertised by OSPF router 2. We will then accurately measure the amount of time it takes for the traffic to converge from the primary path, which is destined to OSPF R1, to the secondary path, which is OSPF R2. Chapter 2. Getting started. As a part of this chapter, we will configure OSPF and the traffic port to be used as a part of the convergence test. For the TrueView convergence measurement, 3 ports are required within an IxNetwork configuration. The first port needs to be configured as the traffic port, or the port which is the source of the traffic. The other 2 ports configured as a part of the test need to be configured as a primary receive port, which is the initial recipient of the traffic, and then a secondary receive port, which is the port that receives the traffic after the failover happens on the first port. To add ports in an IxNetwork configuration, click on the Port Manager tab located in the left navigation window and click on the Add Ports button. Once this button is clicked, the first step that needs to be performed is the chassis which is going to be used for the test needs to be added, and then you select a specific number of ports within that specific chassis to be used in the configuration. For more details on the port manager and port management operations, please refer to the port manager video as a part of the IxNetwork video tutorial. In this example, we've already added 3 ports to the IxNetwork config. The first port, as mentioned, is the traffic port, or the source of the traffic. The second port is the primary receive port, which will initially receive traffic, and the third port is the secondary receive port, which will start receiving traffic once the data plane switchover occurs. The next step in the configuration process is configuring OSPF. To enable OSPF, click on the Protocols button in the left navigation window and enable OSPF on the 2 ports which are going to be used as the test. In this specific test, OSPF is enabled on the primary receive port and the secondary receive port. After OSPF is enabled on the ports, navigate to the Routing Switching Interfaces tab. The first tab within this section is the Protocol Interfaces tab. In this tab, you configure the IP addresses on the IXIA side and the corresponding gateways with the DUT. In this specific example, the traffic port or the source port is configured with the following IP address on the IXIA side and the corresponding device gateway. The same IP address configuration patterns apply to the primary and the receive ports. As you can see in this example, we have 3 IXIA ports connected to 3 different interfaces on the device under test. The next step in the configuration process is to enable and configure OSPF. As a part of this configuration, navigate to the OSPF tab. The first tab in this high-level configuration is the Ports tab. As you can see, we had enabled OSPF on the primary receive port and the secondary receive port. As mentioned in the test topology, there is one emulated router per OSPF port in this case. The next step is to click on the Routers tab. Since one router was enabled on each port, IXIA already goes ahead and creates an emulated OSPF router with a corresponding router ID on each port. Go ahead and enable both the routers on the ports. The number of route ranges by default advertised by each IXIA router is 0. In this example, we'll go ahead and change the number of route ranges advertised by each router to 1. The next step is to click on the Interfaces tab and to go ahead and enable OSPF. So you click on the Protocol Interfaces tab and assign the protocol interfaces that were configured in the previous step to each emulated OSPF router. Go ahead and enable each router. We'll now define the route ranges advertised by each router. In this specific example, since it is a convergence test, we will advertise the exact same route ranges on both the ports. For this configuration example, we'll advertise 1000 routes as a part of this advertised route range. To look at the details on the route, you can always double click on each route range and it will give you very detailed explanation and indication of all the routes that are advertised. Go ahead and enable these 2 route ranges. The difference between the routes advertised on the primary port and the secondary port is that the router emulated on the primary port advertises a route with a lower metric value of 10. The secondary port advertises the same route ranges with a metric of 20. As a result of this, the device under test will always pick the primary port or the router emulated on OSPF R1 or the primary receive port to be the preferred path, since it is advertised with a lower metric. When the data plane switchover happens or the primary receive port becomes unavailable due to an OSPF route flap or a link up or link down event on that particular port, traffic will then go ahead and converge on the secondary receive port because it is a backup path. Now that OSPF has been configured, go ahead and start the protocol on the port. You can right click on the port and click on Start Protocols. To view the protocol state of each of the emulated routers, click on the Statistics tab and the OSPF aggregated statistics. This view gives you protocol information per port. As you can see in this specific example for OSPF, we had 1 session configured per port and both those neighbors are now in full state. In the next chapter, we will now proceed to explain how using this test topology, IXIA will go ahead and calculate convergence times for the TrueView convergence test methodology. Chapter 3. TrueView Convergence. Being able to measure convergence is a critical aspect of testing device performance and availability. Since many new methods reduce convergence times into the milliseconds, specialized equipment is required. These protocols and features need to be validated and tested in a lab with traffic generators and protocol emulators to determine their performance pre-deployment. The most commonly used methods today to determine convergence is to transmit traffic at a known rate, and then when a convergence event happens, there is packet loss. Using the number of lost packets, the convergence time can then be calculated. This is also supported by IxIA as a packet loss duration statistic available per traffic flow. Another commonly used methodology in convergence is high-speed sampling or capture buffers. This method is effective to look at the received delay variation or jitter, but is usually severely limited by the size of the sample or the capture buffer. In the case of a capture buffer, it must be post-processed, which can be difficult and is also time-consuming. These methods are good and widely accepted, but it is important to understand the cause and effect of a failure and reaction time to recover the failure. This measurement is only on the receive side. There is absolutely no correlation to the event that caused the failure. IxIA's TrueView Convergence now provides the most comprehensive convergence test capability in the industry with a new feature called TrueView Convergence. IxIA's flagship software IxNetwork introduces this feature in the version 540. In an effort to provide comprehensive measurement of the convergence, several measurements are required from the IxIA side. Every packet needs to be timestamped. We need to timestamp the first packet in and the last packet out per flow per port. IxIA now has the unique capability to capture the hardware-based timestamp on a protocol event. This same timestamp can then be captured on a link event such as a link up and a link down. IxIA's TrueView convergence methodology also has the unique capability for users to define configurable rate thresholds. IxIA then monitors the receive rates and the timestamp per receive port per flow when the thresholds are crossed below and above these user-defined values. And as mentioned before, we also have the ability to timestamp link events like link up and link down. Using these key capabilities, IxNetwork can now provide complete convergence times from a triggering control plane event to the data plane switchover, which is known as CPDP convergence. We also have the capability to determine data plane convergence, which is the amount of time it takes in the microsecond or the millisecond range for data to failover or switch over from a primary port to a secondary port. We also have convergence calculations to give you ramp up and ramp down times. We will explain the detailed formulae and explanations of each key convergence measurement in the following chapter. To perform these measurements, as mentioned before, a minimum of 3 ports is required. In the traffic options, the CPDP measurement must be enabled, and we will cover these configuration options in the next chapter. One critical piece is when configuring traffic in IxNetwork, tracking per destination endpoint and destination IP must be enabled. This enables for the convergence measurement for each and every destination IP address, and IxIA's TrueView convergence can then be used to calculate accurately convergence per flow or per destination endpoint. Before getting into details on TrueView convergence with the help of a detailed example, I'd like to explain some terminology. Certain terminologies you will see used through the remainder of this tutorial are indicated in this slide. The first is min-ATT. This is the minimum value of the hardware timestamp when a flow exceeds the user-defined throughput threshold, that is the above threshold timestamp. This measurement is performed on the secondary port because the secondary port is what is receiving traffic when the traffic is ramping up from a primary to a secondary port and it exceeds the threshold timestamp. The second value, which is the max ATT, is the maximum value of the hardware timestamp when a flow exceeds the user-defined throughput threshold. That is the above threshold timestamp measured again on the secondary port. There is a min BTT and the max BTT, which are minimum and maximum values of the hardware timestamp when the flow drops on a primary port below the user-defined throughput threshold. The min BTT and max BTT, as mentioned again, are measured on the primary port. There is also the event which is triggering the convergence to occur from the primary to the secondary port, which is known as the T event, or the timestamp of the event when a control plane event such as an OSPF route flap, which will be used in this example, or a link down or a link up event which triggers the data plane switchover occurs. These specific terms will be used in the remainder of the chapters. We will now illustrate TrueView convergence with the help of an example. In a typical convergence scenario, you have a primary port and a secondary port. In this specific example, rate is plotted on the y-axis, and you see that the primary port is receiving traffic and the secondary port right now is not receiving any traffic. In a very typical convergence scenario, you have an event which then causes traffic from the primary port to stop receiving traffic and traffic from the secondary port to start receiving traffic. This event in this specific topology is represented by the marker which is known as T event. This triggering event could be a control plane event such as an OSPF route flap or a link down event on the primary port. In this specific graph, you can see that traffic is now stopped flowing from the primary port as it ramps down for the first traffic flow from receiving traffic at a user-defined threshold all the way to it not receiving any more traffic. And in this example, the secondary port then ramps up and starts receiving traffic for traffic which was originally a part of the primary path. IxNetwork now gives you the capability to measure different hardware timestamps at different points during this convergence test. The first hardware timestamp that is calculated in this specific scenario is known as the T event timestamp. This, in our example, is going to be the OSPF route flap event. We also record then the timestamp which is the min BTT. This is the minimum value or the value of the hardware timestamp for the first traffic flow that falls below the user-defined threshold. We also calculate the value of the last packet timestamp, which is the value that the last packet was received for a particular flow on a particular port. Since this is the first flow in the convergence test, this is going to be the minimum value across all the flows configured within the test. We also calculate the timestamp for the secondary port when the first flow exceeds the user-defined threshold. This is the minimum value of the above threshold timestamp. We also calculate the first packet timestamp for the first flow received on the secondary port. This is the min of the first packet timestamp. The graph here again is representative of the hardware timestamps that are captured for the first flow running between the test. IxNetwork now monitors these same timestamps for each flow running between the traffic test. As a part of the convergence calculations, the other values that are needed to calculate the CPDP convergence times are these corresponding timestamps for the last flow in the traffic test. We then go ahead and monitor and capture the values for the below threshold timestamp, the last packet timestamp, the first packet timestamp, and the above threshold timestamp within this test. Theoretically, the max BTT or the below threshold timestamp, which is the maximum within the test, should be for the last flow used between the test. Correspondingly, the max ATT should be the hardware-based timestamp when the last flow running between the traffic in the traffic test crosses the user-defined threshold. The same applies to the max of the first packet timestamp, which is the value of the first packet timestamp for the last flow converging on the secondary port, and the max of the last packet timestamp is the value of the last packet which is received on the primary port for the last flow running in the test. Based on these captured timestamps within the test, IxNetwork 540 gives you a number of predefined convergence calculations in the 540 release. These four calculated values of convergence are as follows. The first is the DP-DP convergence or the data plane convergence. This calculates the convergence time for the first traffic flow in the test to converge from the primary to the secondary port. This is the value of the smallest hardware-based timestamp on the secondary port which exceeds the user-defined threshold minus the value of the smallest timestamp on the primary port which falls below the user-defined threshold. So based on the previous graph, this is the minimum value of the secondary port ATT minus the minimum value of the primary port BTT. The next convergence calculation as a part of IxNetwork 540 is the CPDP convergence. This convergence time calculates the amount of time it takes from the triggering control plane event, such as an OSPF route flap, BGP withdraw, or link up down, all the way to the data plane switchover for the first traffic flow converging on the secondary port. Based on the graph we just looked at, this is the minimum value of the secondary port ATT, which is indicative of the first flow on the secondary port which crosses the user-defined threshold minus the hardware-based timestamp of the triggering control plane event. IxNetwork is the only application which now monitors and is capable of monitoring these triggering control plane events as well. The next set of predefined calculations are the ramp down times and the ramp up times. The ramp down time, which applies to the primary port, calculates the ramp down time for the primary port as it ramps down from dropping the first packet flow till it stops receiving all traffic. Based on the previous graph, this is the difference between the max of the primary port last timestamp, which is the time at which the primary port receives the last packet for the last flow, minus the min of the primary port BTT, which is the timestamp when the first packet flow falls below the user-defined threshold. The ramp-up time on the secondary port calculates the time for the secondary port as it ramps up from receiving the first flow until it starts receiving all the traffic. This is the max of the secondary port ATT, which is the hardware-based timestamp for the last flow on the secondary port, which is indicative of when all the traffic flows have converged, minus the min of the secondary port first packet timestamp, which is the hardware-based timestamp when the first flow is received on the secondary port. So these are the 4 predefined calculations available as a part of 540. Chapter 4, Convergence Options. In this chapter, we will walk through the options which need to be enabled in IxNetwork to enable TrueView convergence and the CPDP measurement statistics. To enable the convergence mode in IxNetwork, you need to navigate to the Traffic Options tab present in the left navigation pane of IxNetwork. You then move to the Statistics Configuration tab. In this tab, there is a specific checkbox to enable CPDP or control plane to data plane convergence. Depending upon the convergence measurements that need to be made, the user can select one of the following options. Control plane events. If this checkbox is enabled, IxNetwork will monitor control plane events which trigger convergence to calculate control plane data plane convergence. Control plane events in our specific example will be the OSPF route flap, and we want to monitor the hardware timestamp when this triggering control plane event occurs, so we will go ahead and check this box. Enabling this box also monitors events such as link up and link down and the corresponding timestamps associated with these events. The next checkbox is the data plane events rate monitoring. Enabling this checkbox enables users to monitor the rate on the receive port and calculate and capture the timestamp values for the above and below threshold timestamp based on this data plane threshold set. In our specific example, we'll set the data plane threshold value to 100%, which basically means we want to capture the timestamp when the packet is completely stopped receiving on a particular port as opposed to the threshold value where it ramps down. Network also has the capability to measure the packet loss duration statistic, which is another popular method to calculate convergence. In this specific example, we will not enable the packet loss duration, but a user has the capability to measure packet loss duration and the TrueView convergence all at the same time. So to sum, in this specific example, we are monitoring the control plane events, which for us is an OSPF route flap. We are monitoring the data plane events or the rate monitoring, which essentially monitors the receive rate on the primary and the secondary port to calculate the above threshold and below threshold or ATT and BTT timestamps, and we are setting the data plane threshold to a value of 100. Chapter 5, Building Traffic. In this chapter, we'll go ahead and configure traffic and the tracking options required for TrueView convergence measurement. To configure traffic, navigate to the Traffic tab and launch the Advanced Traffic Wizard. For details on the Advanced Traffic Wizard, please review the IxNetwork video tutorial on the Advanced Wizard. In this specific example, we'll go ahead and send traffic from the traffic source port, going to the 2 OSPF emulated routers on the primary port, as well as the secondary port. Since this is an overlapping address range, since the advertised route ranges across both the routers are essentially the same, Network is smart enough to go ahead and detect that there are overlapping route ranges and create just one traffic stream which will be sent to the DUT, and then the forwarding decision based on which port the traffic is to be received on is then made by the device under test. We will leave the packet and the QoS options the same, flow group setup options, frame setup and rate setup as defaults. We'll then go ahead and navigate to the flow tracking tab. This flow tracking capability is a critical piece in measuring convergence. As you can see here, IxNetwork detects that the CPDP convergence measurements have been enabled. In this specific example, it is critical that the IPv4 destination endpoint is selected as a tracking option. For all convergence calculations, it is mandatory that the destination endpoint tracking option be selected. For increased and superior accuracy, we also recommend that the additional tracking be switched on a specific field in the packet that generates the maximum number of flows. In this specific example, it is the IPv4 destination address because there are 1000 flows as a part of the test. Increasing the number of flows increases the accuracy of the convergence calculations because all the hardware-based timestamps are tracked per flow or per PGID, and having additional granularity in terms of the number of flows gives us a lot more accuracy in terms of the calculations which are provided by IxNetwork. Once these options are configured, you can go ahead and click Finish. This will then go ahead and build the traffic streams. You can then go ahead and apply this traffic to the hardware. Once the traffic has been applied to the hardware, you can go ahead and start the traffic for the specific test. In the next chapter, we will cover details on how to view the statistics to get the convergence calculations. Chapter 6, Statistics. To view the convergence statistics, go ahead and navigate to the Statistics tab and view the aggregated traffic item statistics as the first level of aggregated statistic. Again, for details on the statistics, please refer to the IxNetwork video tutorial for advanced statistics. As you can see, for this traffic item, the DUT is forwarding all the traffic that has been sent to it. To get details on the forwarding path for the specific traffic item, you can go ahead and drill down and look at the aggregated statistic for the destination endpoint. This destination endpoint view is the aggregated view across all the destination endpoints, which in this case is 1000 routes within the specific destination endpoint range. This level of aggregation is where IXIA measures and gives you the measurements for control plane data plane convergence and data plane convergence. To view the actual traffic flow, you can go ahead and drill down from the aggregated destination endpoint view to the per R export view. Now, if you look at this resulting view, you will see that the primary port is receiving all the traffic and the secondary port at this stage is dead and it is basically not receiving any traffic. We'll now go ahead and trigger the control plane event which causes the data plane switchover. To trigger this specific event, we'll go back to the test configuration tab, navigate back to OSPF and go ahead and disable this route range as advertised by the primary port. Once this route range is disabled, navigate back to the statistics tab. You will see that at a particular stage, because of the route flap, a certain number of frames were lost. You can now drill down from the aggregated traffic view to the per destination endpoint view to view the values of the control plane data plane convergence and the data plane convergence. In this specific example, if you look, the data plane to data plane convergence time is 28,526 microseconds, which is also 0.02 seconds, and the CPDP convergence time, which is the amount of time it took from the triggering control plane event, which in this case was the OSPF route flap, is 0.8 seconds. You can then go ahead and drill down from the destination endpoint view to the per R export view to view the ramp up and the ramp down times for the primary and the secondary port. In this specific example, the ramp down and ramp up times for the primary and the secondary port are in the order of about 4 seconds. The ramp up and ramp down times are significantly larger than the CPDP and DPDP convergence times because they take into account the amount of time it takes for the IXIA port to go ahead and withdraw all the routes from the primary port. We also have very clear timestamps on when and how long it basically took for the triggering control plane event, which in this case was an OSPF route range disable. We give you timestamps for the start of the event and the end of the event. In this specific case, you can see that the amount of time it took for IXIA to withdraw all the 1000 routes was in the order of about 2 seconds. So using these statistics, it is very easy for someone to go and look at the CP-DP and the DP-DP convergence times and the ramp up and ramp down times of the ports. In order to account for end users who want to use their own convergence calculations, we also expose all the raw packet timestamps per flow in the flow statistics view. So you can come in, navigate to the right, and you will see all the above threshold, below threshold, event start and event end related hardware based timestamps. The user then has the ability to go ahead and export this to a CSV using a single click. You can go ahead and create a new CSV file, and once that CSV file has been created, using filter functions within Excel, you can go ahead and calculate the min and max of all the above and below threshold timestamps for each flow and calculate your own convergence. Using TrueView IXIA positions itself as the only vendor in the industry who's capable of measuring TrueView convergence from control plane to data plane events. This feature is extremely powerful in terms of calculating convergence times with a tremendous amount of accuracy, as all convergence calculations are based on IXIA's hardware-based timestamps per port, which are in the nanosecond range.
For more information on IxNetwork, check out www.ixiacom.com. Thank you for your time and interest from the IxNetwork product management team.